Welcome viewers to the fifth lecture for the online series of lectures for the course of General Relativity. In this lecture we will start our discussion with the concept of covariant derivatives. So we are going to discuss covariant derivatives, a very important notion in general relativity. So first, motivation and notations. A few words about notation. So take a function f belonging to the space of smooth functions, real valued smooth functions on M. So the partial derivative of this smooth function f is denoted by f comma mu, okay, which is defined as the partial derivative of this function. So how partial derivative of function on a manifold is defined, we already discussed earlier, right? We have seen it in earlier lectures. So this is actually the component of a one form. We already know what a one form is. That is, so if I restrict this one form to a point on the manifold, we get a covector, and we expand, or we basis expand this covector in the coordinate basis, right? It's an n-dimensional manifold, sorry. So this is restricted to P. Okay. And we get dfp nu dx nu at P. These are the coefficients of the basis expansion, and we have seen that this is nothing, we have seen in earlier lecture that this is nothing but the partial derivative of this function at the point P, right? And this is by the definition of the partial derivative of a function on a manifold in terms of chart given by this expression, right? Where phi is a corresponding chart. Okay. So for this thing, that is del f by del x nu evaluated at P, if you want to write it this way, these are the components of the covector df restricted to P, right? We can restate this fact by saying that the gradient, the partial derivative of a scalar function, is a 0,1 tensor. Okay? So the gradient of a scalar function is a 0,1 tensor. Good. Now, so let me erase everything. Now observe that the partial derivative of the component of a one form Okay, so by component, I have to explain it. So component is well defined for covectors. So when you have a covector, it is associated with a certain point of the manifold. The covector belongs to the cotangent space. The cotangent space at a point on the manifold. And when you take a particular covector in that cotangent space, then you can basically expand that, and you have the coefficients of that linear combination. Those are precisely components of the covector, which are just real numbers, right? So component of a one form is not actually well defined. So by component what I mean here is that if you have a one form, you can always write it like this, right? So by component I mean these functions, okay? So I needed to clarify it before writing the component before writing what I mean, before introducing this notion of component of a one form, okay? But this is not actually very mathematical to call component of a one form. We can talk about component of a covector, component of a tangent vector, but I should not call component of a vector field or a component of a one form. But if I do that, I mean these functions actually, right? Okay, so now the point is that these guys don't transform like a tensor. The partial derivative of this guy. So the partial derivative of the components of a one form don't transform like a tensor. Okay, so I'm trying to evaluate this guy, right, in a given chart on the manifold. Say that this is the chart, and we are trying to find so these are functions, trying to find the partial derivative of these functions. And if we try to do it, let's try to do it. It's so in x prime mu chart, we write the partial derivatives as omega prime mu del omega prime mu by del x prime mu. Okay. It's in the prime coordinate system, and it can be written down as del x sigma by del x prime mu del by del x sigma by the application of chain rule. We can do it, right? And we know how the components of this one form transform under change of coordinates, right? We have seen it earlier, and using that knowledge, we write omega prime mu as del x rho by del x prime mu omega rho. Okay, now applying Leibniz rule for derivative, we see that del x sigma by del x prime mu del x rho by del x prime mu. So this guy is going to hit this one first to obtain del omega rho divided by del x sigma, and then you have omega rho del x sigma by del x prime mu, and then this is going to hit this derivative now, del square x rho del x sigma and del x prime mu. Okay, Good. So we arrive at the following. We've found that this is equal to del x sigma del x prime mu del x rho del x prime mu del omega rho del x sigma plus omega rho del x sigma by del x prime mu del square x rho del x sigma del x prime mu. Okay, the second term, disrupts everything. Okay, and the presence of this second, problematic second term confirms that this partial derivative of the component of a one form, which we denote by omega rho comma sigma, so this is contributed from the partial derivative, okay, this index, and we put a comma before that. Okay, this was the original component of one form that we are trying to take partial derivative of, and this thing does not transform as a 0,2 tensor. Okay. This does not transform as a tensor. Okay, so we have seen that partial derivative is not good enough, because the partial derivative of objects like components of one form or components of vector field, they don't act as tensors. So we need to find a different kind of derivative that acts as a tensor. Okay, so that's why we need this idea of covariant derivative. So let me define the covariant derivative first, and then we'll list some properties, some important properties of it. Okay, so let me erase everything here. So here goes the definition of covariant derivative. If one denotes the space of local vector fields on the differentiable manifold M as this calligraphic X of M, then nabla is a map. Nabla is defined as a map. Nabla from calligraphic X cross calligraphic X to calligraphic X by, so you see that, so there is a pair here, a vector field on M. Both X and Y are vector fields, and they are mapped to another vector field here, which is nabla XY. Okay, one goes in the subscript and on the side of the nabla of this operator. Okay, so this is again a vector field living in this space. Okay, and this map enjoys the following properties. The covariant derivative, this is called the covariant derivative. The covariant derivative enjoys the following properties. One, so see that X is a vector field, right? So when this vector field acts on a function, a smooth function, a real valued smooth function on the manifold, and it gives you a new function. So X acting on F spits out a new function. But if you put F in front of this vector field, you still have a vector field. From this point of view, we say that the space of a vector fields is a C infinity M comma R module. Okay, so it's a generalization of a vector field, because the underlying ground field is replaced with a ring now, which is the C infinity M comma R thing. Okay, so let us not move into the algebraic details of such spaces or such constructions or such objects. So from what we have discussed so far, we see that this fx plus gy, where x and y are vector fields and f and g are smooth functions on the manifold, real value smooth functions on the manifold. This fx plus gy is another vector field, and z is a vector field. So this whole thing is supposed to be a vector field from the definition of this covariant derivative map. Okay, so and this is equal to f nabla x z plus g nabla y z. So where f and g are both real valued smooth functions on a manifold M, and these are three vector fields on the manifold. Okay. So the second property states that nabla x y plus z is equal to nabla x y plus nabla x z. The third property tells us that nabla x fy. Okay, here fy is another vector field, so it's legitimate to talk about nabla x fy, right? Because fy is again a vector field given the smooth function f on the manifold and y a vector field. Okay, so this, according to the third property, is f of nabla x y, something like Leibniz here. It's again Leibniz, and well, xf. Okay, xf is a function. Okay, xfy. Okay, now we have a small remark concerning the definition that we have just given. If y is a 1, 0 tensor field, that is a vector field, that is a vector field, then so here is another object which is nabla y. So given two vector fields, we can form nabla xy, which according to our previous discussion is again a vector field, and we can also construct objects like nabla y, which is not a vector field, which is a 1, 1 tensor field. Okay, so bear in mind that there are two different things using the same nabla. This is a vector field. This is a 1, 1 tensor field. Okay, so then nabla y can be considered a 1, 1 tensor field. Okay, that is, so initially y was a 1, 0 tensor field or a vector field. After the action of this nabla from the left, it becomes a 1, 1 tensor field. So it increases the covariant index of the tensor field by 1. Okay. So from that point of view, it's called, covariant derivative because it increases the covariant index by 1. Okay. That is, nabla increases the covariant index by 1 in the following way. So nabla y, according to what we have discussed so far, is supposed to be a 1, 1 tensor field, right? This is 1, 1 tensor field. And okay, if it's a 1, 1 tensor field, then according to the definition of a tensor field, we know that if it acts on a one form and a vector field, it's going to spit out a number. How this number is defined? So we have to construct a number out of this expression or out of the data we have on the left hand side. So eta is a one form, and if so it's not going to give a number because it's a tensor field. It's acting on a one form and a vector field. It's supposed to give you a scalar function. Okay, so we'll get a scalar function. Okay, if we were talking about tensors, we would have got a number, but now we are talking about tensor field, so we'll get smooth scalar function on the manifold. So eta is a one form. If it acts on a vector field, then it's going to give us a scalar function, a smooth function on the manifold. Okay, so how do we get it? So this is how it's defined. So nabla x, y is a vector field we know, and this is how it's defined. Okay, this map, nabla y is defined. Nabla y is a 1, 1 tensor field that, upon acting on a one form and a vector field, spits out this scalar function. This is our equation number 1. This is a smooth function on the differentiable manifold. Okay, good. That is eta nabla x, y. Well, this is a smooth function on the manifold, real valued smooth function on the manifold, and this acting at the point P on the manifold should give us a number, right? And that is given by eta at P from the definition of the tensor field on a manifold, right? Eta restricted to P acting on this vector field restricted to P. This is a number, right? This is a number. Because this is a covector because we have restricted the one form to a certain point of the manifold to get a covector. This is a covector acting on a tangent vector. Good. Okay, so out of two vector fields, using the map nabla, we have been able to construct a vector field or a 1, 0 tensor field and a 1, 1 tensor field, right? That we have defined here. Okay. So let me erase everything. I need room. So we denote this 1, 1 tensor field by nabla y, okay, given y is a vector field, and it has component and it has components nabla y mu, right? It's a one tensor field. That's why it has two components, one contravariant index and the other covariant index. It is also denoted by, in the sequel it will be denoted by y mu semicolon mu, okay? In contrast to y mu comma mu. This was partial derivative of y mu with respect to x mu, right? This is del y mu by del x mu. So in contrast to this comma, we have a semicolon here that denotes these components of the covariant derivative. Okay. Now consider equation 1 again. What was equation 1? Equation 1 was, the definition of this 1, 1 tensor field, which upon acting on this one form and the vector field was defined by this one form acting on this vector field. And this implies, in the component form, we write it as eta mu nabla y mu, and then you have x mu. Okay, so it's a scalar, right? We have already defined it as a scalar because on the right side we have a scalar. And on the right side we have eta mu nabla xy mu, because this is a vector field on the right according to the definition of this map nabla, right? From xm cross xm to xm. Good. So what do we see from here? We see from here that this guy, nabla x, y, the new component, the components of this vector field should be equal to nabla y mu x mu. Okay? Or in other words, if you want to use this semicolon notation, it reduces to y mu semicolon mu x mu. So this is the very important relationship between these two objects, nabla xy and nabla y. Remember that given these two vector fields x and y and this map nabla, we can construct two distinct objects. One is nabla xy, which is going to be a vector field, and another object is nabla y, which is a 1, 1 tensor field. And the relationship between the components of these two objects is given by this expression. Okay, this is our equation number 2. This is a very important relationship. Okay. Now, another definition, another very important definition. Okay. So, in the literature, nabla is also called a connection, okay? Covariant derivative or connection, okay? Okay, so now, in a coordinate basis, del by del x mu running from 1 to n, on the manifold M, okay, on the manifold M. So we fix this coordinate fix this coordinate basis on the manifold M, and we see that for two given vector fields we can construct another vector field like this. Okay, so now my question is, if I take these two vector fields to be the coordinate vector fields like this, or the basis vector fields, okay, in the basis vector fields that we get in the coordinate basis. So we are looking at something like this. Where instead of x and y, we are taking these basis vector fields in the coordinate basis. Okay, so what is it? It is supposed to be another vector field, right? So so in the coordinate basis we can expand it in this way. Right? These are the basis vector fields, right, in the coordinate basis. So we can always write it like this. So the components, these are the, well, again, so the way we are calling components of vector fields or component of tensor fields, in that sense, these guys are called components of connection nabla. Components of connection nabla, where nabla is called the connection, underlying connection. Okay, so now nabla x y is going to be equal to nabla. Now I'm writing x in this coordinate basis as x mu del by del x mu. Okay, and I'm writing this vector field y in the coordinate basis as y mu del by del x mu. Okay, now using the properties that we listed, the three properties that we listed in the beginning of the lecture, we can write it as x mu comes in front, right? First of all, x mu comes in front, and then we have nabla del by del x mu, and then we have y mu del by del x mu. We're going to apply Leibniz now, and that gives us x mu, and then y mu nabla del by del x mu del by del x mu plus x mu, and then this operator is going to hit this one, and by the third property we have listed earlier, it is going to give us del y mu by del x mu, right? And then I have this operator del by del x mu. Okay, which is equal to, I leave it as it is here, x mu y mu nabla del by del x mu del by del x mu. Well, I think I have to change it a bit. I need some space. Let me erase this top part. Okay, so from here we go there. This is equal to, well, from the definition that we provided earlier in equation number 3. So get back to equation number 3 where we define the connection components. Okay, using that definition of connection components, we'll prove later in this lecture that those connection components are precisely the critical symbols that we derived using, using the variational principle, right? By maximizing the proper time. We'll see that later in this lecture. But for now, so we are going to apply equation number 3 here to see that this is gamma sigma mu. This is gamma sigma mu del by del x sigma. Okay, so where we are using this definition, nabla del by del x rho del by del x mu is equal to gamma mu rho del by del x mu. Okay, so we're using this definition of connection components. Okay, and then we have this thing which we leave as it is, x mu del y mu by del x mu and del by del x mu. Okay, so now this is again x mu y mu gamma sigma mu del by del x sigma, and for this one, see that here mu is a dumb index, so we replace mu with sigma without any problem at all, without loss of generality. So this is x mu del y sigma del x mu del by del x sigma, and then we factor out the operator del by del x sigma to end up with x mu well, I bring it first, this command, x mu del y sigma by del x mu, and then I write this thing which is x mu y mu and then gamma sigma mu del by del x sigma. Okay. Okay, so we were trying to write, so what are we writing? We're writing this, right? Nabla xy, which is a vector field. Well, then it is supposed to be nabla x, y, sigma, right? Because nabla x, y is a vector field. These are the components of this vector field, and these are the basis vector fields. Right? So this has to be this thing. So the vector field, the components of this vector field is given by del y sigma by del x mu plus gamma sigma mu y mu times x mu. Right? Now remember, I gave you the relationship between these two objects, nabla xy, which is a 1, 0 tensor field, and I gave you nabla y, which was 1, 1 tensor field. Then I had this relationship, very important relationship between these two objects given by equation number 2, which was stated like this: nabla x, y, mu is equal to y mu semicolon mu times x mu, right? So now if I use this, then it is supposed to be, if we choose the proper indices, if I put x mu here, then I should have y sigma semicolon mu here, right? Or using this nabla symbol, this is going to be nabla y sigma mu, right? Okay, so let me erase these things so that we now have y sigma mu, which is the same as nabla y sigma mu, sigma mu, right, which is the same as nabla y sigma mu, and this is equal to precisely this, nabla y, so del y sigma by del x mu, the partial derivative of this function y sigma, which is of course a function, not a scalar function, plus gamma sigma mu, and then we have y mu. Okay, so this is again a very important relationship which we number equation 4. So which sometimes is written in the literature as y sigma semicolon mu, and this is the partial derivative of y sigma, which we denoted by comma earlier, right, plus this connection components sigma nu mu y mu. Sometimes it is written like this. They are synonymous. Now I give you an exercise. Here is an exercise for you. Consider a change of basis. Consider the following change of basis. The following change of basis, del by del x prime mu to be equal to del x nu, del x prime nu, and then del by del x nu is the relationship between the prime coordinate system and the unprimed coordinate system. And show that under such basis change, this connection components are sometimes called connection coefficients, right? Gamma, rho, sigma, tau, these components, they don't change as tensor fields. In other words, these are not 1, 2 tensor fields as they appear to be. This was one of the questions in the last pop quiz. Okay, but you got to prove it now. Okay, so let me erase everything. Now, along the same line, nabla can be defined on tensor field. So we have seen that nabla acting on a vector field gives us a 1, 1 tensor field. Right? Y was a 1, 0 tensor field, and after the action of this nabla on Y, it raises the covariant index by 1 to result in a 1, 1 tensor field. Right? This guy is a 1, 1 tensor field. But now the question is, if I can hit it, this nabla operator on a general tensor field T, we can actually, right? And we can easily do it using Leibniz property. If T is a tensor field of type R, S, then nabla T is going to result in a tensor field of type R, S plus 1, raising the covariant index by 1 here as well. Okay? So now we're going to do it for one form. So we did it for 1, 0 tensor field or vector field, and we derived the components of this 1, 1 tensor field. Right? And so saw the explicit expression of this, right? In terms of the partial derivatives, and there we had this connection components appearing in the explicit formula. But now we are going to do it we are going to hit it on one forms instead of vector fields. Let's see how it goes then. For example, if eta is a one form, you can also call it covector field. Okay. Then for any two vector fields, one defines nabla x eta. What is it supposed to be? It's supposed to be, well, you see that in the same way as nabla x y was a vector field given x and y two vector fields. So if nabla x acts on eta, it is supposed to give us another one form. So if it acts on y, then it is supposed to give us a scalar function, right? And that scalar function is defined as nabla x I don't want to write it like this. X nabla x, see that this nabla x acting on a scalar function is nothing but by definition is simply xf, okay? Simply x acting on f, which is a function. So nabla x acting on this scalar function eta y minus eta, which is a one form, acting on this vector field nabla x y. So this is the function. We are good. This is again a function by this thing, right? And this is on the left side. We have this guy to be a new one form, And when that one form acts on this vector field y, it also gives us a scalar function. So on the left side we have a scalar function, on the right side we have a scalar function. So we are good. So that is what we end up with is as follows. Nabla x, this guy, acting on eta y is equal to this thing, nabla x eta, which is another one form. This guy acts on the vector field y to give a scalar function, and that gets added to this expression, right? Eta nabla x y. Okay, this is what we have. Okay. Well, this is not yet very clear why nabla eta is a 0,2 tensor field, right? It is supposed to be a 0,2 tensor field. Why? Because eta is a 0,1 tensor field, and after the action of this nabla on eta, we are going to have this covariant index increased by 1 to result in a 0,2 tensor field. So let's see how that happens. Okay, let me erase everything here. Let us write down what we have defined a little earlier. Nabla x eta, which is a one form acting on this vector field y, was defined as nabla x eta y minus eta nabla x y, okay, which is equal to nabla x. Well, this scalar function, I'm going to write it as using the components nabla eta y, eta mu y mu, okay. This is a scalar function, and then writing this scalar function, the whole scalar function, as eta mu nabla x y mu. Okay, so now using Leibniz, right? Leibniz property of derivative operators or covariant derivatives. X, so nabla x eta mu, okay, which is the same as we have seen that when this nabla x acts on any function, okay, that spits out xf, right? So this is going to give us x eta mu, right? Eta mu is a function, and then we have y mu, and then we have eta mu, and then we have x y mu. Then I have a minus sign here, eta mu, and we know how it looks like, right? We have defined it earlier. Using that expression, we can write it as x nu del y nu del x nu plus the connection components gamma mu rho nu, and then y rho x nu. Okay, so we have derived it earlier, right? Okay, now since x in the coordinate vector field, we can write this vector field in the coordinate basis, we can write this vector field as x nu del by del x nu. Okay, so that one gets nabla x eta y is equal to x acting on this function eta mu, and then we have y mu minus, I've written down this command first, and then does anything cancel anything? No. Okay. Okay. See that if we use this guy here, don't we have this cancelled out against this? Yes, we do, right? So that we are left with this and that, right? So this is x eta mu, y mu, and then we have eta. So let me write this connection coefficients first. Gamma mu, rho mu, and then this eta mu, and then I have x nu and y rho, right? This is good. Okay, this term cancels against this term by the application of this expression. Good. Now this is going to be equal to x eta mu, y mu, and then gamma. So I am interchanging mu with rho here, okay? Because rho is a dummy index and mu is also a dummy index. I'm changing these two dummy indices, okay? So that so I have rho here, mu down here, mu here, then I have eta rho here, then I have x mu again, then y, this is y rho, it's going to be y mu. So that now I can factor out y mu from this expression to have x acting on eta mu minus gamma rho mu mu eta rho x mu times y mu. Okay. Now it is supposed to be what? This guy. So see that nabla x eta is a one form, and that is acting on this vector field to give a scalar function, right? And that scalar function should be something like this, right? In terms of complement. Now this is a one form. The mu component of this one form is given by this, and the mu component of the vector field is given by this. So that this is precisely this object, right? So then here is this top part to create some room, so that we have nabla x eta mu to be equal to x eta mu minus gamma rho mu eta rho x nu. So I think it's good. Okay, so we know that we have seen earlier that we can write this as x nu del by del x nu in the coordinate basis, right? So that's what we are doing here. X nu del eta nu by del x nu minus gamma rho mu nu eta rho x nu, so that this turns out to be del eta mu del x nu minus gamma rho mu nu eta rho times x nu. Now, what is this? This is the long desired 0,2 tensor field, right? Nabla eta mu nu, because so let me erase this bottom part now. So we have found out that nabla nabla eta is a 0,1 tensor field, and nabla eta is going to be a 0,2 tensor field, and this 0,2 tensor field is given by this expression, right? Del x nu minus gamma rho mu nu eta rho. So this is also denoted by eta mu semicolon nu. Eta mu is the component of the one form that we are trying to derive, and nu is coming from this covariant derivative operator. Okay, so that we have found that eta mu semicolon nu is equal to eta mu comma nu minus gamma rho mu nu eta rho. This is how we get this 0,2 tensor field, explicit expression of this 0,2 tensor field, or the covariant derivative of a one form, resulting in a 0,2 tensor field. Okay, good. This is our equation number 5. Good. So let us take a break here. Then in the next section we will try to give you the general formula for the covariant derivative of a general R, S tensor field. Thank you for attending this first segment.